Hey, this is Dr. Sweeney. What we're going to be looking at today is we're going to be looking at something called elementary row operations and generating row-echelon form. Elementary row operations and the generating of row-echelon form and reduced row-echelon form are really critical to doing Gaussian elimination and Gauss-Jordan elimination for solving systems of equations. They're kind of fundamental to linear algebra. And basically they're a process. So what we're going to be looking at today inside of this video is that process, the process of our elementary row operations and that generating a row-echelon form. Okay, so we'll first start out with this idea of row reduction. And so row reduction is going to be the process of transforming a matrix into a row equivalent form using the use of row operations. And when I talk about a row equivalent form, what I'm talking about is a matrix generated by these row operations, which we'll get into in just a second in more detail. So a matrix can have literally an infinite number of row equivalent forms. And a row operation is a transformation performed on a row of a matrix either by another row in the matrix or by a scalar or both. So let's take a look at row operations in a little bit more depth. We have three basic row operations. The first one is going to be called permutations. And what that is that's switching two rows inside of the matrix. The second one is called multiplication. And that is multiplying one of the rows by a scalar multiple. And then the third one is called addition, and this is adding a scalar multiple of a row to a scalar multiple of another row. So let's look at some examples of these row operations. Let's suppose that I have this matrix A, and A is 2, 3, negative 1, 4, 1, 2, 1, negative 1, 4, and it's 3 by 3. Now what I'm going to do first is I'm first going to do this thing called permutation. And with permutation, what I'm going to do is I'm going to switch two rows. In this case, I'm going to permute row 1 and row 3. And I'm going to write that in my notation. I'm going to call it P13. And so what that means is that the first row becomes the third row and the third row becomes the first row. So my new matrix is going to be 1, negative 1, 4, 4, 1, 2, and 2, 3, negative 1. And that's my first row operation. I can interchange any two rows inside of the matrix. My second operation, we'll call this multiplication. And it's a scalar multiplication. And let's say, for example, I want to multiply row 2 by 4. Okay, so I'm going to multiply row 2 by 4. And what it's going to give me is it's going to be 1, negative 1, 4, because I keep the first row exactly the same. Then I'll have 1, 1/4, 1/2. Because that's what the second row would be if I multiplied it by 2. And 2, 3, negative 1. I'll oftentimes, by the way, by 1/4. Our next operation is called multiplication. And let's say, for example, that what I want to do instead of this new matrix, this matrix right here, I'm going to multiply the third row by 1/2. That is that I want to make the 2 into a 1. So I'm going to write this. Sometimes you might see it written as multiply row 3 by 1/2, or a notation that I use too is 1/2 times row 3. And now what will happen is that row 1 and row 2 are going to remain exactly the same. 1, negative 1, 4, 4, 1, 2. But now row 3 is now going to be multiplied by 1/2. So we get 1, 3/2, negative 1/2. And there we go. The third is addition. And this is adding two rows. And so let's say, for example, that what I want to do is I'm going to take row 2 and I'm going to add negative 4 times row 1. Essentially what I'm going to want to do here, and we'll talk about this in just a little bit more depth, is I'm going to want to make this second row first column into a 0. And so I'll add those two columns together, and what I'm going to do, I'll do my work on the side. So I have 4, 1, 2, that's row 2, minus 4 times 1, negative 1, 4. And what I get, 4, now minus 4 times 1, that's 0. 1 minus 4 times a negative 1, that's 5. And then 2 minus 4 times 4, that's going to end up giving me negative 14. So now my second row here, row 2, is now going to be 0, 5, negative 14. And so only the second row is going to be changed in this case, and my other rows will stay the same. And so that's my third row operation. So I've got permutation, I've got multiplication, and I've got addition. Let's take a look at how we utilize these in order to do row echelon form. We'll get a lot more practice on this in just a second. Now we're going to be transforming matrices into what's called row echelon form. And you want to think about transformation of a matrix into row echelon form as kind of like a game. The goal of the game is to turn something into row echelon form, which we'll get into, and the rules of that game are row operations. So we'll use those row operations in order to transform any matrix into this thing called row echelon form. The row echelon form is as follows. 1, all 0 rows will be at the bottom of the matrix. And what a 0 row is it's a row that's made up of only zeros, no other values other than 0 in the rows. 2, the furthest most left value in any one non-zero row is a leading 1 or a pivot. 3, the elements below any leading 1 are all zeros. So to give you an example, this matrix right here, the identity matrix, is in row echelon form. But also, we could have an upper triangular matrix like this also be in row echelon form. So these are both in row echelon form. On the other hand, a matrix like this is going to be not in row echelon form because its row of zeros is at the top instead of at the bottom. Or, so this is not, we might have something like this. In this case, this value right here is a leading 1 or a pivot. We have no zeros below that leading 1 or a pivot. You may actually see some places transform matrices into row echelon form where they don't have this requirement, that is that you have a leading 1. Instead, they'll think of a pivot as the furthest most number. So for example, you might have right here, you might see a 2. And then below that 2 is a 0. What that's saying though is there's no numbers to the left of the 2. And below that furthest most left number, we have only zeros. And that's also a version of row echelon form. I'm actually going to utilize this definition here because it's the one that I've just used all the time. It's the one that actually is most valuable for turning something into, for using Gaussian elimination or Gauss-Jordan elimination. All right, now what we're going to do is we're going to use row reduction to transform a matrix to row echelon form. And here's the basics of this process. This process is pretty surefire. It eliminates a lot of the thought process that goes on to doing row reduction. And inevitably, it ends up being the most efficient way to go through and solve systems. We use it for Gaussian elimination and Gauss-Jordan elimination. So here's the process in a nutshell, and then we'll do a demonstration. 1, we're going to create a leading 1 in the furthest most non-zero column. Then 2, we're going to use addition to reduce all values below that leading 1 to zeros, if they're not already zeros. Then we'll move down to the next row. Then we'll multiply the next row by a scalar to create the next leading 1. Then we'll use addition to zero out below the leading 1. And we're going to repeat that process until the matrix is in row echelon form. So let's take a look at the example that we had before. Let's say that what we had is we had the matrix 2, 3, negative 1, 4, 1, 2, 1, negative 1, 4. The first thing that I want to do by my process is I'm going to want to create a leading 1 in the furthest most non-zero column. And I'm going to do that by permuting 1 and 3. We did that earlier. So I go in, I permute 1 and 3, I get 1, negative 1, 4. As my first row, 4, 1, 2. And now my last row is 2, 3, negative 1. Now I'm going to use row operations, addition specifically, in order to zero out the rows below. And that 1's going to come in very handy. Because what's going to happen is we're going to first start it with like row 3 minus 4 times row 1, which is what we did before when we did addition. Okay, so this gives me 1, negative 1, 4 at the top. And now I'll just use a little scratch area, 4, 1, 2 times, and this will be negative 4 times 1, negative 1, 4. 4 minus 4 is 0. 1 minus 4 times negative 1, so that's 1 plus 4. If we look at it, that's going to be a 5. And then 2 plus negative 16, that ends up being negative 14. So this is now 0, 5, negative 14. 2, 3, negative 1. Now I want to zero out the third row, or first column, third row. And so how I'm going to do that is I'm going to use row 3 and I'm going to subtract 2 times row 1. Again, because 2 times row 1 is going to give me 0. Right? You can see that if I take 4 minus or 4 plus negative 4 times 1, that gives me 0. If I take 2 plus 2 times, or negative 2 times 1, that also is going to give me 0. So you can see that 1 comes in very handy. Now I'm going to do a little math, back of the napkin. 2, 3, negative 1, and this is going to be negative 2 times 1, negative 1, 4. And so what I end up with is, 2 minus 2, that's 0. 3 minus 2 times negative 1, and that's going to end up giving me 5. And then negative 1 minus 8, that's going to give me negative 9. And so my new matrix is going to be as follows. It'll be 1, negative 1, 4, 0, 5, negative 14, 0, 5, negative 9. And there we go. Now, what you may notice here is you may notice that these two, that's a 5 and a 5. And if you're doing the process of row reduction and you're used to doing row reduction, we may not actually have to go in and scalar multiply. We'll talk about that in just a second. If we were to go through and do the next step in the operation, what we're going to do is we're going to multiply 1/5 times row 2. So I take 1/5 times row 2 and I get 1, negative 1, 4. 0, 1, negative 14 over 5, and 0, 5, negative 9. Done. Okay? And that's the next step. We've now created a leading 1 inside of our second row. Now I'm going to use addition to zero out below that leading 1. And so that's going to be row 3 minus 5 times row 2. Okay? And so just a little scratch work, 0, 5, negative 9, negative 5 times 0, 1, negative 14 over 5. We get 0, 0, and then this ends up being negative 9 plus 14, so that ends up equaling positive 5. So we have 1, negative 1, 4, 0, 1, negative 14 over 5, and 0, 0, 0, 5. Now, just to finish this out, for my version, I'm going to create a 1 in that third row. So I'm going to take 1/5 times row 3, and I'm going to get 1, negative 1, 4, 0, 1, negative 14 over 5, and 0, 0, 1. And there we go. Notice we have no rows of zeros, no 0 rows. But if we go up, the furthest most left value in any row is going to be a 1, and then we have zeros below. Right? We have the 1, zeros below, and then of course a 1 here in that third row. So this is in row echelon form, and we write that as the REF of A. Let's take a look at another example now. So we have this matrix. It's 2, 3, negative 1, 4, 1, 2, negative 8, negative 2, negative 4. And so what we're going to do is we're going to row reduce this matrix. So the first thing we want to do is we want to actually create a leading 1 in this furthest leftmost element inside of the matrix. In this case, we don't have any ways to permute. So what we're going to do is we're going to multiply. We're going to take 1/2 times row 1 to make a 1 in that first slot. So I get 1, 3/2, negative 1/2. Everything else remains the same. 4, 1, 2, negative 8, negative 2, negative 4. Then what I'm going to do is I'm going to take row 2 and I'm going to subtract 4 times row 1. Okay, so I've got 4, that's 4, 1, and 2 minus 4 times 1, 3/2, negative 1/2. So this is going to be 0. 4 minus 4 is 0. Now we have 1 minus 6. So this is going to be negative 5. And then we'll have 2 plus 2, and that's going to end up being 4. So our new matrix is going to be 1, 3/2, negative 1/2, 0, negative 5, 4, and then -8, -2, -4. Then again, I'll zero out below that leading 1. So I'm going to take row 3 minus, or rather plus 8 times row 1. And doing a little bit of math here, I got -8, -2, -4 times, and this will be 8 times 1, 3/2, -1/2. We'll add those two together. I get 0. This will become -2 plus 12. So that's going to be 10. And then -4 minus 4, and that's going to be -8. So now what we get is our new matrix has 1, 3/2, -1/2, 0, -5, -4, or excuse me, -5, 4, 0, 10, -8. Now what I want to do is I want to create a leading 1 instead of the second row because I've now got leading 1 in the first column and 0's below it. So I'm going to multiply -1/5 times row 2. And you may be asking yourself, can I just take 10 or row 3 plus 2 times row 2? And that's absolutely allowed. Totally fine. I'm just kind of following my process. So that's going to give me 1, 3/2, -1/2, 0, 1, -4/5. And then now what I need to do is I need to end 0, 10, 8, -8. That doesn't change. And now what I need to do is I need to zero out below that leading 1. So I'm going to get row 3 minus 10, row 2. So that's 0, 10, -8, and then 0, 1, -4/5. And we'll multiply that by -10. And that gives me 0. And this also is a 0. So we have 0, 0, 0. So now I have 1, 3/2, -1/2, 0, 1, -4/5, and 0, 0, 0. Notice now I do have a 0 row. It's right here. And that 0 row is at the bottom of the matrix. And if you're doing my process is going to give you your 0 rows at the bottom of the matrix every time anyways. But if it wasn't, you'd actually have to permute it down to the bottom in order to transform it into row echelon form. We'll notice that I have a leading 1 in the 2 other non-zero rows, and then I have 0s below that leading 1. So this is now the REF of, call this matrix B. That's the row echelon form of B. The last concept that we want to go over inside of this video is we want to go over this really important idea of the rank of A. And the rank of A is going to become absolutely crucial to everything that we do in linear algebra. So what the rank of A is, it's pretty simple. It's the number of non-zero rows in the REF of A. It gives us an incredible amount of information. Okay? So what we need to do in order to find the rank of A is we first need to row reduce down to either the row echelon form or the reduced row echelon form. And then we're just going to go in and count the non-zero rows. So for example, in our first example, we got this for our REF of A. And so if we notice, we have 1, 2, 3 non-zero rows. So the rank of A is equal to 3. If we look at our second example, we can see that we have 1, 2 non-zero rows. The third row here is a 0 row, so it's not going to get counted. So the rank of B is going to end up equaling 0. Is going to end up equaling 2. One more example. Let's suppose that we have the matrix C, and this matrix C is 1, -1, 2, 3, 5, -2, 6, -2, 1, 5, 4, -3. Now this isn't actually in the REF form, so I'm actually going to transform it, and I'm going to get the REF of C is going to equal then 1, -1, 2, 0, 1, -1, 0, 0, 1, 0, 0, 0. And when we look here and we count out the number of non-zero rows, we have 1, 2, 3 non-zero rows. So the rank of C equals 3. And that's the idea of rank. Pretty simple idea. You're going to see it a lot. Super duper important. And that's what we mean when we say it. All right, let's review the big ideas from this video. 1, row reduction is going to be the process of transforming a matrix to row echelon or reduced row echelon form using elementary row operations. To do that, we're going to have 3 basic elementary row operations. 1, permutation, 2 multiplication, and 3 addition. We know that we've got something in row echelon form, or a matrix in row echelon form, if all the 0 rows are at the bottom of the matrix, all non-zero rows have a leading 1 or a pivot, and the elements below each pivot are all zeros. The rank of the matrix is going to be the number of non-zero rows then in the REF of A. So if I want to find the rank, I'm going to have to first row reduce either down to the REF or the RREF of A, and then count the number of non-zero rows. Hey, I hope you enjoyed watching the video. I know I enjoyed making it, and I really just enjoy teaching linear algebra in general. If you did enjoy it, go ahead and click on the thumbs up button. If you got a lot out of it, also click on the thumbs up button. If you have a comment, or if you want to ask a question, or if there's a particular piece of math that maybe you want some help on, go ahead and leave that in the comments as well. If you really like the stuff that I'm doing, you want to learn more about linear algebra, differential equations, you want to work on calculus or discrete mathematics or just mathematics in general, please subscribe to my channel.